Isn't it wonderful that almost each and every corner of this vast and wonderful world is merely an arm's length away? Dial a telephone number and you can hear voices thousands of miles away. Had it not been Dr. Alexander Graham Bell's quest for knowledge, this perhaps would not have been possible. And trying to whet your appetites in your quest for trying to know how many things occur, we are back again this week with this week's edition of your favorite inter-school science quiz quest. Conducting a lot of very interesting experiments for you, we have the director of Nehru Science Center, Mr. G.S. Rautela. Let's have a big round. How are you doing, sir?
Fine, thank you.
Enjoying Calcutta?
Yes.
Wonderful. Let me introduce the teams to you. On my right is the J.C. Bose team, and you are?
I'm Ronak Pandya from Apeejay School.
I'm Vivek Arya from Apeejay School.
I'm Nikunj Jhunjhunwala from Apeejay School.
Welcome. And on my left is the C.V. Raman team, and you are?
Hello, I am Surjit from 𝐶𝐞𝐬𝐿 Fort William.
Hello. Hi, I am Sudeep from 𝐶𝐞𝐬𝐿 Fort William.
Hello, I am Inul Shah from 𝐶𝐞𝐬𝐿 Fort William.
The rules of the contest not very much different from every week. 7 questions in all, 4 of them are direct. The first 4 are direct, that's to each team 2 questions each. 20 points for correct answers on directs and 10 on passes. 15 seconds to answer every question. Unanswered questions go into the audience. So I think, Mr. Rautela, we are ready for the very first of them?
Yes.
Right, so the very first question is for the J.C. Bose team. So Apeejay School, that's the J.C. Bose team. Are you ready for your first question?
Yes.
Mr. Rautela, over to you.
The first question, I need a volunteer. Is there anyone in the audience?
Why don't you come up? What's your name?
My name is Orko Shen. I am from Apeejay School, class 12.
Okay, Arko, I would like you to touch these 2 plates with your 2 hands together and tell me which one is cool, which is warm.
This is cold, this is not cold.
It's warm.
Yes.
Okay. So you agree that this metal plate is cooler than the wooden block. Now both of them are in the same room having the same temperature. The question to you is, why do you feel a difference?
The difference is because the steel plate conducts the heat at a much higher rate than the wooden plate. The steel plate is a better conductor of heat.
Yeah.
So when we touch it, we feel the heat coming into our hands more readily than
From
the
the
wooden
metal?
plate. From the metal, than the wooden plate.
No, from the wooden plate.
Would you try?
Yes, sir. Sir, in the steel plates, when the heat is falling, it gets reflected. But in the wooden plate, it gets absorbed. So therefore, when we touch the steel plate, we get we feel cold. But while in the wooden plate, we feel hot.
Why the temperature?
So wooden plate is insulator, sir.
Yeah.
And the steel plate is an conductor, sir.
From where is getting reflected the heat?
From the surface, sir.
Anyone in the audience is not a quite correct answer. Anybody in the audience?
Orko, let's have a volunteer coming back here. Yes, Orko, please come. Hold the mic.
As we know, that steel is a much better conductor of heat than wood.
Yeah.
So when we touch it, heat from our hand is flowing into the steel.
Right.
And so as the heat is going out of our hand, we feel the cold.
Yeah.
The wood does not conduct the heat. So it stays in our hand and we feel the heat only.
Yeah, that's the correct answer.
Good answer then, Orko. We have a small memento for you from Quest.
Thank you.
Thank you. Please. Neither team scoring on the very first question. The next question goes for the C.V. Raman team. And now with the scores reading love all, that's no score to either team. We go over to the C.V. Raman team. Are you ready?
Yes, sir.
Mr. Rautela?
The question is, you have a burning candle inside water here. Now I have a jar. I'm going to place this jar over the candle and see what happens. Once again.
My intuition says that. मेरे को faces देखना.
You saw the water going up in the jar. Can you tell me why does it happen and why the bubbles came out of this?
So as you press up that jar in the water jar, bigger volume, the air inside the jar get dipped in the water. They take the place of water, and as the air come up, the air gets come up in the form of bubbles.
Now, why does the water rise up in the jar?
So it is due to Archimedes principle.
Would you try?
So because the oxygen is used up in the jar when the candle is burning, the oxygen is used up as a result.
That's the normal answer everyone gets, but that's not quite correct. Where does the carbon dioxide go?
Huh? Hold it.
So it escapes as the bubbles.
No, but it's not because of the oxygen burning up.
And also the water is formed along with the carbon dioxide. A part of it is used up to form water.
Can you form water just with oxygen and carbon dioxide?
No.
No, I think that's not a correct answer.
Not with oxygen, carbon dioxide. So in combustion, water and carbon dioxide will be formed. The carbon dioxide remains part, but the water part gets exhausted off.
From where?
It is used up.
Oh, whole oxygen is used?
Not the whole oxygen, sir. The water part. In combustion, you have carbon dioxide and water.
Okay.
The carbon dioxide will take up a volume, but that will be smaller than the original volume of the oxygen.
Carbon dioxide heavier than air. Anybody in the audience try?
Any takers in the audience? Don't see any. Mr. Rotella, I guess you'll have to do the honors.
Well, it's true that the oxygen is used up for burning the candle for a while when the jar is inverted on that, and that is a normal answer everyone gives. But that's what happens to the carbon dioxide which is formed. That also remains inside the jar. So, but you must have seen while I was placing the jar, few bubbles came out. That came because of the heated air inside. Because of the candle heats up the air inside the jar, and those bubbles are pushed out. The air is pushed out. As a result, there is a partial vacuum inside the jar, and the water rises because of that. That's the real analogy. Whereas in our textbooks is always written that it's oxygen which is taken away by burning candle, and 20% of oxygen is, so 1/5 of water rise in the jar is because of the the oxygen used up from the air. But that's not the correct answer of it. Okay.
Interesting theory that, Mr. Rotella. Both teams yet to get off the mark, and we're going to be back with the next question, which is for the JC Bose team. Both teams firmly anchored to the starters block. No score so far. JC Bose team, your turn.
Okay, the question for JC Bose team is, there's a newspaper and there is a stick which is strong enough. It doesn't break very quickly. Now I'm putting this stick under the newspaper. Okay, with little eye out, projecting out. When I slowly hit, the paper lifts up. Okay, once again, when I slowly press the stick, the paper lifts up. But when I hit it hard, the stick breaks. The question to you is, such a light paper on the top of the stick, how does it break, and why not the paper does not tear?
So because when we apply force on it, sir, so at first time we were applying the force, the time taken by us was more than the second time. So there's an impulse which was formed, sir.
Also there is the air above it. When you're lifting it up slowly, it curves in this way. When you hit it hard, the paper tries to come up at once, and because the pressure of the air is there and the area is quite large, As a result, the stick breaks.
No, not very accurate answer. Would you like to try?
When we are hitting it too hard, it is facing an impulse force. So the rod which we have given the force, it has no that it can't understand the force, the impulse, as it's the impulsive force. It's a very little time we are giving the force to it. So it is not coming up to the mark, sir.
No,
Sir,
not
may I
accurate
have a
answer.
try, sir?
Pardon?
Yes, Surjit, go ahead.
Yeah.
Yes, so when so in the first time when you press that stick slowly, so the air get inside that, and so the paper comes out slowly. But sir, at the next chance when you hit it very hard, so the pressure in upside of the paper is very low, very high. So and pressure inside is very low, and due to this Bernoulli's principle applies on that, and therefore it gets break out.
Or
No, too complex method you are thinking.
Both the
Anybody-
teams, I think, are complicating themselves. And the answers. Any takers in the audience? Yes? Why don't you come? Hold the microphone. Yeah.
Hi, I'm Manish from KV Fort William.
Yes, please come behind there.
Well, I think the correct answer is that when you hit it very hard and large impulse is applied on it, so it is given very small amount of time to break. So the force applied is very large. Compared to the previous one, the time allowed to break was very large. So force applied on it was very less.
No, that's not the correct answer. Anyone else in the audience?
Yes, why don't you come? You can go back. Yes, you are?
Hi, I'm Chandra Banerjee from Sri Shikshatan.
Yes, please come.
I think the correct answer is that when you heat it slowly, it gets much time. It is both of them are at rest. It gets much time to raise the paper, and when you heat it hard, it gets less time. So, due to inertia of rest, the paper can't go up, and the stick breaks there.
Partially correct. I think I'll try to put the, she talked about inertia, that's a very important factor here. Okay, I'm just adding to her answer. When the stick was under this, when I was lifting slowly, the force which I was applying can transmit. It gets time enough to transmit towards the paper, so it can apply the same force to the paper to lift up. But the second case, when I was very quick, there was no time for the force to transmit quickly, so rather it sheared the paper, this stick and the paper, because of inertia, remained there. And one more factor is important here, the atmospheric pressure applied on the paper is much higher. The area, if you can calculate, and how much will be the atmospheric pressure, such a big amount of pressure is also applying on the paper, all right? So that was the transmission of the force, one factor, and the atmospheric pressure, another factor.
Do you think she has the right answer, Mr. Rotella?
Yes. I think we should give her something for the big applause for her partial correct answer.
Okay, please come. A small memento for you. Both teams yet to score. The last of the decks is for the C.V. Raman team. Mr. Rotella.
Well, your question is, I have a glass here. I am going to fill it up with water to the brim. And place a paper on the top of this. And take it inside. And take out the paper out of it. Now, when I lift this, the glass, the water doesn't empty. The question to you is why the glass is not emptying, dropping the water, and how high I can lift it if the water column is sufficiently high. How high I can lift the glass?
As you dip that glass in the tumbler, you have taken out the paper. Some vacuum is created over the glass, and the pressure outside the glass becomes higher, and therefore you have to apply a force to lift the glass.
No, that's not the correct answer.
No, Surjit, that's not the right answer.
We will.
JC Bose team, yes?
So in this case, when you once fill the glass tumbler,
Yeah.
after that, when you try to lift it up, earlier the water was up till the top.
Yeah.
Now when you try to lift it up, a vacuum is created.
Yeah.
As a result of that vacuum, and because the outer atmospheric pressure is much higher, so the water gets forced back into the glass.
Okay.
And
how high I can make this water tumbler?
So
that it
the
will still
tumbler
hold.
is large enough. Then just like so the barometer. In a barometer you have mercury, and it's up to the 76 centimeters height.
Yeah.
Now once you, if it's the barometer is say this tumbler is a long tube, and then it will because the pressure, outside pressure, if let's say we consider it to be 76 centimeters of mercury, so then the water can be lifted high to about 76 into 13.6, because the relative density is 13.6 of mercury.
Okay. So that's the correct answer. It will be 10.34 meters.
Very good answer.
So they get 10 bonus points.
Well done, Ronak. You picked up 10 points for your team. Mr. Rotella, do you want to add to that?
Well, you could make a water barometer. Exactly, this is the principle. If you want to make a water barometer, you need a tube minimum 10.34 meters tall. So you can measure atmosphere pressure with water. But that's too big a size. That's why mercury is chosen, because density is 13.6. So your column size reduces to that proportion.
Yes.
And now, the first of the buzzer questions, but first the scores. 10 points to the JC Bose team. CV Raman team, you get to score. Let me explain the rules. They are fairly simple. It's plus 20 and minus 10. Remember, teams, you can hit the buzzer at any point here on onwards, all right? At the point at which you press that buzzer switch, you must have an answer ready, irrespective of whether or not the question has been asked. These questions are not transferable, and they go straight into the audience if you get them wrong. So, Mr. Rotella, here we go.
Well, the next question is, if I take little water in this tumbler and allow it to roll down at an angle, the water clinges to the surface of the glass. But if I tilt it more, the water falls. Can you tell me why does this water clinch to the surface of the glass and not fall down straight away?
Yes, Surjit?
So as the force of adhesion between the water molecules and the glass molecule is more, therefore when you will tilt it in an angle, the water will come up with the glass. And sir, if you pour it straightly.
No, that's not a quite correct answer. Anybody in the audience?
Any takers in the audience? Nobody? Mr. Rotella, I guess you'll have to give us the answer.
Well, I'll have to explain this. When I'm pouring this water, I'm making a stream of water to flow out of the glass. As I narrow down the stream, because the stream is wider at the inside the glass, as it comes to the tip rim of the glass, that stream becomes narrower. Any flowing fluid, when the size reduces, the speed increases and pressure falls down. When the pressure falls down, atmospheric pressure is higher, so that makes the stream to clinch to the glass. But when I am allowing it to fall at a wider stream this way, so that doesn't happen, no pressure falls down and it can flow easily outside the glass. So that's the answer for this question.
Neither team scoring on that one. Scores remain exactly where they were. JC Bose is on 10 points, CV Raman yet to score. But CV Raman team, I do hope you remember it was supposed to be minus 10. But since you've not scored anything, we don't have anything to take away from you. You remain exactly where you were.
Next question, there is a dish which half blackened and half with broken lines. And this is normally known as a Benham's disc. When I rotate this, the black disappears and you see rings, lines, rings on this with colors. Why do we see colors on the disc?
Yes, Indranil?
Due diffraction?
No, that's not the correct answer. There is no diffraction. Anybody in the audience?
Indranil, minus again? Anyone in the audience?
Let me try to give you an answer. Of course, still today scientists believe that the explanation to this is not 100% satisfactory. You must have seen the line, black and lines are also not the same length. So when you are rotating, so these lines give you white light at successive frequencies. So as a result, the light going to your eye is equivalent to the coding that eye has sensitive time for each color. So the eye tries to interpret it as that color because of that time that takes to cut the whole circle. Okay? So this is kind of a coding for the eye equivalent to the color. It has it tries to see the colors. Okay? So what is happening, this line when it cuts off, it completes the circle in different timings. So as a result, the frequency of that one is different. So eye takes it as a color coding for that particular color, and you start seeing that color.
Welcome back. You're watching Quest, the weekly inter-school science quiz. We are into our last question today. Anything can happen. Either of the teams can win or lose. JC Bose's team, you're on 10 points. CV Raman yet to score. Mr. Rautela.
Well, for this question, I need 2 volunteers.
2 volunteers. Anyone in the audience wants to? Yes, why don't you come up? Yes. And in the back, yes. Please come. Come. What's your name?
Hello, my name is Rohit Kedia. I'm from Apeejay School.
Yes, please come in.
And I'm Preeti Khemka from Sri Shikshayatan.
Okay, Preeti and Rohit.
Yeah. Well, I have 3 tubes here. I'm going to fill up powders of various grades, various thickness or granular particles, or you could say size of the particle. Quite fine powder, little coarse sand, and very big particles of sand, gravels rather, you can say. So in the first one, I will request you to hold this, and I am going to fill this powder to this tube. And I would request you to hold this tube.
Mr. Rautela, I'm sure you're not performing some ancient ceremony here, are you?
No.
No. All
The
right.
third one I'm going to take myself.
Okay.
And I fill up the granular particles. Okay. Now I hammer them up a little bit to pack them and open the bottom tape so that the tube is free from the bottom corner. Now I will request you to lift it when I tell you very slowly. I am lifting the first one. Oh, all sand falls down. Now I request you to lift it. Here the sand doesn't fall. And can you lift? Can you lift now? And the powder also doesn't fall. You got it? So the coarse granular sand emptied immediately, little finer sand remain inside the tube, and the powder remain inside the tube. Goes free. Now the question to you is, why doesn't the powder or the finer sand doesn't fall? So buzzer round.
Neither team going for the buzzer. 5 seconds to go. Make up your minds, teams. Good, Indranil.
For the bigger granules, it has more mg, the weight.
Well, if you remember Galileo's experiment in Pisa Tower, you wouldn't say this answer. Particles of the same, whatever with the mass, if you drop together, they should fall together.
Yes, sir.
Anybody in the audience then?
And if our volunteers want to answer? Yes,
I
Preeti?
think since this powder is
Just a
very
moment.
fine.
Why don't you take a microphone? Yes, start again.
Since this powder is very fine,
Yes.
when you put this in the tube, it is very compactly arranged.
Yeah.
There's very little space in between.
Yeah.
And since these are bigger grains, there is a lot of space in them. So when you lift it up, it falls down.
But why not the powder? It's free to fall.
Because it's just like the arrangement of molecules. When they're compactly arranged, it is solid. And just like these grains are compactly in a compact thing, so they don't fall down.
Well,
There's
well
very little
tried.
space.
Anybody else would like to give a better answer? I think I would add to the correct answer. Here something is called sliding friction. Okay, smaller the particle, the sliding friction is bigger, higher. So the particles which are bigger in size, the friction was much lower. As a result, they fell down. And whereas this, as you go in the size smaller in the granules, the friction increases, and mass of each particle is also less. That friction can hold that mass together, and as a result, doesn't fall down from the tube. Okay.
Well, Mr. Rotella, that certainly did fall down. Volunteers, you can go back to your places. You can leave that alone.
That should be cut.
Yeah, I know. Well then, that brings us to the end of today's episode of Quest. The final score tally, 10 points to the Apeejay School, that is the JC Bose team. Let's have a big round of applause for them. Well done, boys. Thank you for coming on to our show. Ronak, Vivek, and well done. Well, you tried many questions and were not able to get some of the right answers. C.V. Raman team, that's the Central School from Fort William. Thanks for coming on to our show. Big round of applause for them. Indranil, Surjit, and Sudeep. Well, we hope you had as much fun in watching this show as we have had in making it for you. We'll see you again next week with another episode of Quest. Our address, please write back to us, is Quest, care of Doordarshan Kendra, 18/3 Uday Shankar Sarani, Golf Green, Kolkata 95. We'll see you again next week with 2 new schools, that's 6 new faces. Till then, it's goodbye from all of us here at Doordarshan Kendra, Kolkata.